Hi, my name is Mary Jeansson, and it's my pleasure to take you through some of the key points in our recent publication in JCI. Chronic kidney disease can be summarized in 3 words. It's common, serious, and costly. It is affecting 850 million people globally, and it's estimated to become the 5th leading cause of death by 2040. It is expensive and have a high burden on our healthcare systems. It is important to gain mechanistic insight and new treatment options for these patients with a high unmet medical need. Chronic kidney disease can arise from many causes, for example, type 2 diabetes and hypertension. However, decreased capillary density and tubular interstitial fibrosis are 2 hallmarks independent of etiology. Tyrosine kinase receptor TIE2 is expressed on endothelial cells, and its signaling protects blood vessels. TIE2 is activated by angiopoietin-1 that clusters TIE2, allowing for TIE2 activation and signaling. In kidney disease, the antagonistic ligand angiopoietin-2 is upregulated, and this decreases TIE2 signaling. ABTA is a humanized antibody that binds 2 angiopoietin-2 dimers into a configuration that turns angiopoietin-2 into a TIE2 agonist, and this restores TIE2 signaling. Several factors contribute to the loss of TIE2 signaling in kidney disease. Apart from the increase of angiopoietin-2, also VPTP increases, and this results in more dephosphorylation of TIE2. In addition, TIE2 itself decreases. In the current study, we have investigated ABTA as a therapeutic intervention and also utilized endothelial-specific knockout of TIE2 as a kinase dead model. We have used endothelial-specific knockout of VPTP, which will increase TIE2 signaling, as well as a PDGF-B knockout model. The unilateral ureter obstruction model was used to induce kidney injury, and the contralateral kidney was used as a control. In the study, we have investigated kidney injury and the sequence of events in different compartments of the kidney. In the study, we showed that by protecting blood vessels, we can limit tubular injury and ensuing tubular interstitial fibrosis. I will now go through some of the key data from our publication. We measured perfusion of renal vasculature with contrast imaging ultrasound after intravenous injection of micromarker. The UEO model induced a loss of vascular perfusion, which was even worse in TIE2 knockout mice. Both ABTA treatment and knockout of VPTP improved renal perfusion. PDGF-B knockout had no effect on vascular perfusion. We then investigated peritubular capillary density in renal cortex with immunohistochemistry for vascular markers. In this figure, we have used polycalyxin to quantify vascular density. Decreased capillary density is evident after kidney injury and even worse in TIE2 knockout mice. Both ABTA treatment and VPTP knockout prevented loss of capillaries. PDGF-B knockout had no effect on capillary density. In addition to loss of capillaries, peritubular capillaries also lose their fenestrations. Fenestrations can be quantified from electron micrographs. UUO induced loss of fenestrations, which was even worse in TIE2 knockout mice. In contrast, both ABTA treatment and VPTP knockout prevented loss of fenestrations. Tubular interstitial fibrosis is the final step in kidney disease injury. We measured fibrosis in renal cortex by immunohistochemistry for alpha-smooth muscle actin. Fibrosis was induced by UEO kidney injury and worsened in TIE2 knockout mice. In contrast, ABTA treatment and VPTP knockout reduced fibrosis. Knockout of PDGF-B also reduced fibrosis. So what is the connection between blood vessels and tubular interstitial fibrosis? It has been suggested that endothelial cells can undergo endothelial mesenchymal transition, and we investigated this in the current study. We utilized an endothelial lineage tracer, in pink in the figure, together with a nuclear PDGF receptor alpha reporter, in blue in the figure, and the PDGF receptor alpha reporter marks mesenchymal cells. As expected, mesenchymal cells increase in fibrosis. However, they never overlap with the endothelial lineage. Our results show no evidence for endothelial mesenchymal transition as a mechanism for fibrosis in our model. We also investigated tubular injury in our model. TIE2 knockout had detrimental effects on tubular injury and worsened the injury, while both AMTA treatment and VPTP knockout protected tubular cells. RNA in situ experiments show that injured tubular cells start expressing large amounts of PDGFB while reducing angiopoietin-1 expression. We can also see the increase of PDGFB in injured kidneys with qPCR or ELISA. And importantly, ABTA treatment and VPTP knockout both reduced PDGFB. As expected, PDGFB decreased in PDGFB knockout mice. Next, we investigated the early response in kidney injury starting 6 hours after UEO. It is evident that tubular injury, represented by upregulation of KIM1, PDGFB, and loss of angiopoietin-1, happens very quickly after injury. Endothelial TIE2 is also affected very early. In contrast, at these early time points, there is no mesenchymal activation, in this case represented by PDGF receptor beta, suggesting that mesenchymal activation is a later event. Studies show that healthy blood vessels are critical for tubular cells. This is perhaps not a surprise, as these cells have a high energy demand to carry out their function. The injured tubular cells start producing pro-fibrotic factors, including PDGFB, and mesenchymal activation and fibrosis will commence. Others have shown that this step can be therapeutically targeted by reducing PDGFB signaling. However, vascular injury is not improved in our PDGFB knockout mice, suggesting that this is not a viable approach in the long run. Instead, restoring TIE2 and vascular function has beneficial effects in all compartments.